Ooh, that's bright. All right, I know you'd really rather just chat, but instead I'm going to force you to listen to me. I promise I'll be short. I'm Christopher. I'm one of the co-founders of Anoma. I have a confession, which is that I'm not a real cryptographer. It let me into this event by mistake. If you remember the schedule that Awa showed, there was this, these first three talks were all about cryptographic schemes, and then there's like Anoma, and then there's Julio's talk. And that is, I don't know if intentionally or not, but brilliantly accurate because Anoma sits in between cryptographic schemes and applications as kind of an architecture for tying all of these things together and allowing these two parties to find each other. So I'm going to talk about Too Much Crypto, all in Anoma. Well, this talk had this title somehow that, I don't know how it got that, but it was going to have another title of Too Much Crypto in the Dark Too Many Vampires in the Dark Forest of Tyga, Too Much Crypto in Anoma. But I was told that was too many characters, so instead it's a subtitle. But I'm going to talk mostly about two parts of the Anoma protocol stack, which has too many names as well, but two of those names, you only need to know about two of the names, the too many crypto in the Anoma stack today, and they are Tyga and Vampire. And I will explain what those are in the rest of the slides, or at least I will try. So brief overview of this talk. What is Taiga? Why bother? Sounds complicated. There will be some, so instead I promise to spare you diagrams involving or like mathematical equations involving groups and fields, but instead I have color-coded data flow diagrams involving like intent gossip and partial ordering data flow. You may like those more or you may hate them more, but at least they're different. I will talk a little bit about, then most of the talk will be on how Taiga works and sort of architecturally what Anoma does and how it uses cryptography and how we try and use like simultaneously as much and as little cryptography as possible. And then at the end, I will talk about Vampire, which is our attempt to solve this problem that all of these crypto schemes don't have any users, and all of these people writing programs don't get the latest crypto schemes by intermediating this relationship with compilers. And do I have anything on future research? Maybe, you'll find out. Okay, Taiga and Vampire, both, I should note here, are a part of the Anoma project, which is built by Helix, particularly the Tyga team. They do all the real work. I just give talks, complain about stuff. So, Taiga is an architecture for private counterparty discovery and settlement. And those terms might not be super familiar, so I'm going to explain what they mean. But mostly I'm going to focus on counterparty discovery because privacy and settlement is easy, and you already know how to do it. Just as a quick survey of what you know, so I can avoid explaining things that won't be interesting. How many people have heard of Zexi? Raise your hand. How many people have heard of Vera Zexi? Keep your hands up. How many people have heard of Tyga? Go home. Okay. All right, so why bother? Tyga. So distributed networks so far have done what we call in the Anoma Lexicon of naming things programmable settlement. That started with the first generation, basically Bitcoin, Namecoin, colored coins, stuff like this. Scriptable settlement, Bitcoin opcodes, very simple things, no state, not Turing complete is this weird red herring, but not sufficiently programmable for most applications. Then generation 2, Ethereum, Cosmos, other programmable L1s, Near, Solana, et cetera, brought programmable settlement. And in particular, those of us who care about privacy were very excited when Zcash launched featuring private settlement. So settlement layer means like settlement happens when you already know who are participating in which parties are participating in a transaction and what they want to do. So basically settlement is like, here's a transaction, settle it, order it on a distributed ledger, allow people to verify that it has been ordered, maybe verify what some of the results were. Sounds great. Also, privacy in settlement layers is easy because there's like one class of observer. There's a settlement layer and people observe it, and you care about privacy to like all of those observers who are in the same class. So when we think about privacy in Zcash, you just say, oh, like, look, there's a transaction on the Zcash ledger. What does the observer learn by seeing that transaction on the ledger? They learn, in case of Zcash, quite little, which is great. But in counterparty discovery, so why do we need counterparty discovery at all? Settlement happens when parties already know who they are and what they want. But as we have found out, watching distributed applications be built by people, that is not sufficient. It's actually kind of the easy part that happens at the end. Many applications want to, if you're using permissionless systems and interacting with people who you may not know, particularly, you need to somehow discover them. Like you want to find your counterparties. This is true of basically everything other than like transfers. So it's true of a marketplace where you have buyers and sellers. It's true of something like quadratic public goods funding, where you have projects, you have donors, you have funders. It's true of DAOs where you have voters. And critically, all of these parties want to find each other programmatically. So, maybe there's some like restrictions on identity, like who can make a project in the public goods funding or who the voters in the DAO are, but subject to like identities being qualified in that sense, you want to find, particularly in marketplace stuff or like stuff where you're matching funders and donors and projects, you want to find other counterparties programmatically. So if you do that, in order to find anyone programmatically, you need to reveal some information about that allows that search to happen. And systems are only as private as their weakest link. So if we want privacy for these kinds of complex full-stack applications that need to do counterparty discovery as well as settlement, then we need private counterparty discovery. Therefore, Taiga. Contemporary approaches to counterparty discovery, just to summarize briefly, do it on the blockchain. AMMs do counterparty discovery on the blockchain. On-chain order book, works. Expensive, kind of silly. You're paying for unnecessary ordering, no privacy. Single operator database, this is like most things, OpenSea, Xerox, Relayer, Flashbots, rollups, blah, blah. Depending on whether it's ZK rollups not exactly the same kind of trust, but there's some like trust here, certainly from a privacy standpoint, and you don't, like the operator sees everything that's going on, even in some ZK rollup. In particular, they see, MEV in some sense is information asymmetry from some operators seeing information about the thing that you want to be turned into a transaction before it actually is a transaction. Also, some people have built app-specific sovereign chains or are building them, but it's very expensive. So to avoid unnecessary developer work in the world and to save energy on food to feed developers and go to conferences, we are building a generalized counterparty discovery system based on the concept of intents. So intents are, you could think of intents as like also partial transactions or something prior to transactions. Intents are expressions of the user of what they want instead of how to get it. One realization that we've come to in trying to architect systems for people that involve data structures like blockchains and cryptography is that people, no matter how much we may love to explain this stuff, kind of don't care about how it works. They just want to do what they want, and they want the promises which the architecture is making to them at the level at which they are interacting with it to be satisfied. So that means stuff like privacy, that means stuff like correctness, it means stuff like fairness if you're interacting in some kind of marketplace. And we express this concept in Anoma with intents. So intents are binding programmatic commitments to preferences. Intents are gossiped around a peer-to-peer network. There are entities called solvers who find basically combinations of intents that can be joined together and have all of the intents by the parties who made them individually satisfied when they're joined together. Solvers create transactions, and transactions are settled on the settlement layer, which you can think of as a blockchain. Privacy and settlement is easy because you've already agreed on what you're doing. You already know who the parties are. You just use some ZKPs to prove that it was valid, send the transaction to the blockchain, done. Privacy and counterparty discovery is not, because in order to find your counterparties when you don't know who they are, you must reveal some information. And you need to reveal if we want privacy, we need to find the exact point, reveal as much information as you need to find your counterparties and no more. So with Tyga, how does this work? Here we come to the diagrams. All of these diagrams were made by Yulia, who's sitting in the audience. Thank you, Yulia. And sorry for the abrupt color change, but it's worth it for the diagrams. So basically, very high level, there are intents. Those intents are gossiped around the network. They get seen by solvers who try and combine them together. You will notice that this diagram contains an infinite loop. That is because we exit the infinite loop on an exit condition, which is when we have a final transaction. And the reason there is a loop like this is that we can turn solved intents. You take some solved intents, you take some intents, combine them together, think like A for B, B for C, and you can combine this to A for C, and this is very important for privacy reasons. So Taiga is a zero-knowledge state transition framework like Zexy, or Vera Zexy, so it's built on top of a zero-knowledge proof scheme. At the moment we use Halo 2. And it provides both data privacy and function privacy. So privacy for things in the notes or the state, and privacy for what functions you're actually executing. And in particular, what we want to find a way to do in the Anoma architecture is express intents in Taiga. So when we have an intent, consider the case of Zcash. So when you use Zcash, You want to send a transfer. In your zero-knowledge proof, you prove that you have, like, you create a note of like 5x, and you say that it belongs to Adrian. That's the person you're sending to and the amount, and you have to spend some other note, so you create a zero-knowledge proof that you know some other note that hasn't yet been spent, that is owned by you, and that is like of value 5x. And you put that proof along with commitments, nullifiers, some other metadata to the, in the transaction, submitted to the ledger or the validators or miners, whatever, full nodes, verify the zero-knowledge proof, apply the state changes, sounds good. So all of this is happening prior to that, and instead it's happening in the intent gossip network, and in the intent gossip network, we cannot do all of these things because we don't have the data yet. So if I am Alice and I want a star, no, I want a dolphin. If I'm Alice and I want a dolphin and I have a star, I'm offering in my intent to trade a star for a dolphin. And I can already spend the star note because I know it. So I spend the star note, I put that in the partial transaction, and then I need some way to express the fact that I want a dolphin. In particular, we want to carry forward these, you can think of this as like Alice has some constraints, and Alice wants those constraints to be satisfied in the final transaction. But Alice doesn't yet know all of the components of the final transaction. In particular, if she wants a dolphin, she doesn't know, she wants like any dolphin. She doesn't know which specific dolphin. There's some specific note in a final transaction that satisfies Alice's preferences. There's some specific dolphin that will be sent to her. But Alice doesn't know what that is yet because she doesn't know who her counterparty is, and because everything is private, she doesn't know, like, you know, the other data in the dolphin, other than that it's a dolphin. So Alice expresses that constraint in something called an intent note. And an intent note creates a sort of imbalance in this transaction that can only be satisfied if a dolphin is sent to Alice. So we encode this using, let me go to the next slide. We encode this using a generalized version of the value balance. So if anyone remembers homomorphic Peterson commitments value balance from Zcash protocols, Sapling, Orchard, we use a version of this that instead is generalized to work with different, you could think of it as different asset types, but generalized all the way to work just with arbitrary messages. So when Alice makes her constraint, a blue square with 1, she creates a special denomination, like it ends up being a unique value base, that can only be balanced out in the final balance check if someone creates another proof that satisfies her constraint and kind of cancels that one with a -1, which is this balancing intent note. So if we think about this outer transaction, the outer transaction is balanced in this world. All of we call these predicates, and it's similar to birth and death predicates or in Zexy, but each node has predicates governing when that node can be created, when nodes of that type can be created, and when nodes of that type can be consumed. Sorry for going really fast here. There's a great documentation page on GitHub, which I will link to if this seems like too much. And we extend the balance check to derive the value base from the predicate. So we basically take the hash of these predicates that is used as like a content address type of the note, turns into the value base, and that's what allows Alice to forward these constraints. So in these individual partial transactions, we have satisfied predicates because we can only like create a proof when we know the predicate and it's satisfied, but we do not have a balanced transaction. And Alice also forwards some data, like she has to forward the pre-image of the predicate that's unsatisfied so that some solver later can create a proof. But once we have all these partial transactions that are compatible with each other, matchable intents, we can combine them together. They just form the final transaction, which is all the predicates are satisfied and it's balanced, as you see down there. So, all right, here's the really big diagram. Phase 1, create intents, intent VPs. Alice has stars, wants dolphins. Bob has dolphins, wants trees. Charlie has trees, wants stars. As you see, there's a circle here. But they don't know about each other yet, so they each create partial transactions. Those partial transactions spend the thing which they have, and they encode in a constraint the thing which they want, so they're not going to be balanced. Then some solver, actually here we did this case of partial solving. Some solver found the first 2, Alice and Bob's partial transactions, and we see already here that we have satisfied Alice's constraint because Alice is going to get the dolphin. So the solver can see that it should send the dolphin to Alice. It will satisfy Alice's constraint. That's like canceled out. That value base is now 0 in the balance check. Then the second solver can come along. The second solver sees this new intent, which has been created by the composition and partial solving, and it combines it with Charlie's partial transaction and creates the final transaction. The reason why I bothered showing you this very large and complicated diagram is that partial solving is very helpful for privacy. So just thinking about what I've shown so far, what kind of privacy do we get in Taiga? Identities who are private, that's pretty easy, but assets, amounts, and constraints, what are public? In settlement, we can make everything private with the final ZKP, but in counterparty discovery, in order for this solver to be able to create this proof that Alice's constraints are satisfied, it must know what Alice's constraints are. And also in order for it to like realize that Bob's partial transaction, Bob's intent, is the one to match with. So in particular, what I wanted to say is that the reason this partial solving is important is that it provides improved privacy. So once we've done the first phase of solving with Alice and Bob's partial transactions, we can combine those because now instead of like star for dolphin and dolphin for tree, it's just star for tree. So we can combine those into an intent which is indistinguishable from one in which, or mostly indistinguishable from one in which, modulo dummy notes and stuff, from one in which someone just wanted to swap star for tree. So the number of participants and what individually their preferences are is now hidden. Yes, the state of Taiga, if you would like to check whether what I showed you is meaningful or just like some diagrams, you can go to this website, GitHub, Anoma Taiga. We have a prototype with Halo 2. It can actually make proofs that take about 2 seconds. We discovered that some of the Halo 2 accumulator stuff was just like written in a paper but not actually implemented, so we've ended up needing to actually implement that, which is what we've been working on recently. There's some simple example VPs. There's one for Sudoku, actually. Proofs can be created and verified. Please don't use it in production, please, please. But it is, one reason we name all these things separately is because we intend them to be used separately by people who just want to do one specific thing, and the interfaces are designed to be very modular and nice. And speaking of modular and nice interfaces, the last part I want to cover in my 3 minutes and 42 seconds is the Anoma ZKP compiler stack. So earlier when I talked about Anoma connecting zero-knowledge proof schemes to programs, the main difficulty here is dealing with all of the users who want to write programs and all of the cryptographers who want to write cryptographic schemes, because users want to write programs and they care about like the abstract properties of the cryptography, what kind of soundness and privacy they're getting, what the protocol does, and they care about efficiency, but they don't care about like the details of the scheme. Cryptography is fungible, modulo security properties and efficiency. Also, we just got really frustrated because at first we started with Plonk, and then there was Ultra Plonk, and then there's Plonk-ish, and then there's like Splonk, Uber Plonk. One of these is real. Sorry, one of them is false. Actually, maybe two. Well, won't tell you, but if you know how many of them are false, there's also Hyperplonk. Yeah, there are more that are not listed. Anyway, I mean, too many Plonks, and there was like a new Plonk every 3 months. And just like, do we need to, we want to use the latest and best cryptography, but I don't. Should the cryptographers like have to update to the newest Splonk Donk Tonk every month? It doesn't make sense. So build a compiler. Luckily, there is some good mathematical structure that informs where you want to actually define the interfaces in a compiler pipeline. And we have built a language called Vampire. Vampire is like LLVM for polynomials and circuits. So if you look at how the rest of the world, which does weird things with von Neumann architecture machines instead of cryptography, works, there are a bunch of languages, they compile to LLVM, and then LLVM compiles to all of the actual architectures, roughly, to summarize things. In our case, we are interested in cryptography, which operates over circuits, and those circuits, like Plonk and Halo 2, different kinds of Starks and Starks, have different specific characteristics. Like they have different gate arities, they have different trade-offs in proof size, prover time, certain complexities. They have different things that you have to do in order to make the circuits efficient. But all of the circuits can be still represented in a way that's semantically equivalent with a higher level IR that just deals in abstract circuits. So one question you might ask is, why not use something which defines a different VM as opposed to building an IR? These are complementary. Not sure if von Neumann architecture is necessary for programs that you always want to terminate because you want to make a proof for them. But something like some of these VMs, at least in principle, could be written in Vampire. Vampire is something that you can use to compile polynomials to specific proof systems. So one way of thinking about this is that we want with Vampire to turn all of these hand-rolled constraint writing tricks, which are amazing and brilliant, but they're very one-off and they require, there are a finite number of cryptographers who can write them in the world. So it would be great if we could turn them into mathematically sound compiler optimization passes, which will take a long time, but seems possible. Also, we did a bit of benchmarking to justify this effort to write an IR, and you could find that at ZKP Compiler Shootout. It has benchmarks now for RISC-0, Plonk, Mine, Halo 2, and we will be adding Vampire, Geb, and Triton. I think there's some Triton people in the audience. Soon, please submit issues and PRs. We're very happy to add new targets as well. Of course, there's some like apples to oranges here. We've tried to be very clear about what is the apples to oranges, what is the apples to apples, how to learn what you care about from benchmarks. But it is useful just to get a sense of the order of magnitudes of things. Yeah, I would say our pitch to cryptographers is that we're trying to build this like compiler stack that works on higher level interfaces and properties and abstracts some of the details from programmers, both so that it's easier to write programs without getting low level implementation details of cryptography wrong, because it's easy to get those details wrong, and so that it's easier to take existing programs which have already been written, if they've been written in this higher level language, and just like snap in the new cryptographic schemes by writing a new backend. Eventually, in some great world that we don't currently live in, but we're trying to move towards, where we can verify that compiler passes are correct using some category theory, we can actually add automated bounties for faster compiler passes, improve this by 10%, 1% extra tokens to you, which seems cool. Thanks. I used 5 extra seconds.